Dear students, we are going to discuss today the maximum power theorem statements, its application, and also we are going to do the mathematical procedure or a process in order to prove the maximum power transfer theorem statement. Now, according to the maximum power transfer theorem statement, what the statement says is a network or a circuit, in a circuit or a network, the maximum power can be delivered from the source to the load when the load impedance is equivalent to the complex conjugate of source impedance. What I mean to say impedance? Impedance is a complex quantity consisting of real part and the imaginary part. The separation or the difference between the real part and imaginary part can be defined in terms of a J. J is nothing but a separator for the real part and the imaginary part. It is similar to your A plus IB. As I we are taking for a current, so we are not denoting or we are separating with a J, where R is called the real part, nothing but a resistance. J is nothing but a imaginary, X is nothing but a imaginary part, which is called the reactance. So the combination of real part and imaginary part is called the impedance, which is called the phasor ratio of voltage to the current. So what your statement says is load impedance is equivalent to the complex conjugate of source impedance, then the maximum power can be delivered from the source to the load. This is a theorem which is applicable for your mobile network, satellite communication system, or any network which is consisting of a source and a load, which is called a source and a destination. So if a circuit or a network or if a system has to deliver the maximum energy or a maximum power, then this condition need to be satisfied. Whatever the information that I am giving, if you want entire information that I am giving, if you want to receive, because I am a source and you are a receiver when I am going for when I am taking a class, then you need to satisfy a condition that you need to concentrate. So the required condition to get to take the maximum information from me, you need to concentrate physically and also mentally in the class. Similarly, for a circuits or for a network, they have to satisfy some theorem that is called a maximum power transfer theorem. So the next means the theorem that we are going to discuss is going to be maximum power transfer theorem. Maximum power transfer theorem. Is the statement is clear? Maximum power transfer theorem. For a theorem we need to prove. In order to prove the theorem, what we will take is we will consider a network as a circuit which is applied with some source. The source voltage of this circuit we are assuming as a complex quantity. Don't worry about for the time being. It is a AC signal or a AC voltage which is indicated in the form of a magnitude and a phase angle. So Vs angle of 0 degrees. For the time being, just don't worry about this. Okay. So we are taking two elements. Now this we are assuming as Zs and another element we are assuming as ZL. What I mean to say ZS? ZS is called as a source impedance. You are very much clear that Zs is going to be a complex quantity whose impedance is consisting of two terms. One is called the real part, another one is called the imaginary part. So it is going to be Rs plus Jxs. The same formula that we discussed, R plus Jx. In place of R, I am writing as Rs. Rs means S means source, R means resistance, source resistance. In place of Xs, X I wrote as Xs. X means reactance. S means a source reactance. Similarly, when I am talking about a ZL is going to be load impedance. So the same story, you know that Z is equal to R plus JX. So ZL is going to be RL plus JXL. It means that whatever the source that you are taking, its resistance is given by RS and its reactance is given by JXS, whose impedance is going to be ZS. ZS is simply equivalent to RS plus JXS. And the load that you are connecting, is going to be a load impedance, having a load impedance. The load impedance is going to be ZL, and it has a resistance which is going to be RL, and it has a reactance which is called as XL. Yes, class. Now what I want to say is, this is nothing but your antenna, or this is nothing but your transmitter having a impedance ZS. This is nothing but your mobile. So all are in a particular loop in the form of all are connected in the form of a loop or in the form of a circuit. Now, how that my load which is going to be my mobile is going to receive the maximum signal from the network or from my mobile tower. So that can be when ZL is equal to ZS star. So that's what when it satisfies a maximum power transfer theorem. Or the condition that is nothing but a ZL is equal to ZS star. That is when the load impedance is equivalent to the complex conjugate of source impedance. With the application of a source, whatever the current that is flowing through this circuit, I am taking in a clockwise direction, and current is denoted with the I. I am saying the source current is going to be IS, which is going to be with an angle of 0 degrees because we are taking a AC. So whatever the current that is flowing through the circuit or a network is going to be IS angle of 0 degrees, which is nothing but current flowing through the circuit. You are very much clear that the total impedance of the circuit, or I can say that I is equal to, I is nothing but a current that is going to be flowing through the circuit. So IS is equal to Vs by Rs. But here we are not taking the I is equal to V by R. You are very much clear. So we are not taking the resistance, we are taking the impedance. So it is going to be Z. Is is equal to Vs by Z. What is the Z? Z is going to be sum of those two. Why the sum? Both are in a series connection. So Zs plus Zl. So Is is equal to Vs, means here we are taking angle of 0 degrees, so it is going to be AC, so it is going to be 0 degrees. So 0 degrees, so by Zs plus Zl. Clear? So here the story is, the current wait a minute class. The current flowing in the circuit can be written as so there is a story. Now substitute the expressions of Zs and Zl. So Is angle of 0 degrees is equal to, there is an expression. So Is angle of 0 degrees is equal to Vs angle of 0 degrees by, you know that Zs is equal to Rs plus Jxs. So Rs plus Jxs plus RL plus JXL. Now my expression I can write as Is angle of 0 degrees is equal to Vs angle of 0 degrees by, now writing the denominator in terms of a real part and a imaginary part. So my real term is going to be Rs plus RL plus J into XS plus XL. Is it clear? Right? Now this is the current that is flowing through the circuit with the application of source Vs angle of 0 or with the application of a AC source. This is the expression of the current. I don't want this expression, I want the maximum current. Because your maximum power transfer theorem says that maximum power delivered to the load by the source. So the maximum current flowing through the circuit is, I am denoting the current as I. So I am saying as Im is nothing but a maximum current flowing through the circuit. So the maximum current can be obtained by taking the modulus of the Is angle of 0 degrees. Is angle of 0 degrees. So Im means what I want to say is if I take the modulus of this, what I am going to get is nothing but a maximum current. So modulus of Is angle of 0 is going to be Im. So Im is equal modulus of Vs angle of 0 degrees by x plus jy or x plus iy or a plus a plus ib. If I take the modulus, it is going to be a square plus b square square root or square root of a square plus b square. So we can write as Rs plus RL whole square plus XS plus XL whole square. Means modulus of a complex number. The complex number is going to be a plus ib. The modulus of a plus ib is simply equivalent to square root of a square plus b square. So that's why this is a term and this is going to be b term. So it is going to be Rs plus RL whole square plus XS plus XL whole square. Are you clear with me, class? Yes? Now the modulus of Vs is going to be simply Vm. So I can write my expression as, so Im is equal to Vm by square root of Rs plus RL whole square plus XS plus XL whole square. Is it clear, class? Now the theorem is not saying about the maximum current. The theorem is saying about the maximum power. Now when I go for the power, now we'll write in the form of a note. So we know up to this extent what do you mean by voltage, what do you mean by current, what is the formula of a voltage and what is the formula of a current, how to find out a current and how to find out a voltage. If I take the product of voltage and current, that means if I am taking the product of voltage and current, that is Vi, it is simply equivalent to P. So the power is simply product of voltage and a current. You are very much clear that V is equal to IR. V is equal to IR. This is from the Ohm's law. So if I substitute that, it is going to be I square into R. So P can be I square into R. Or I can write as V I is equal to V by R. So then if I substitute this expression, it is going to be V square by R. That means if I know the expression of the current or the value of a current, square it and multiply with a R resistance, what I am going to get is nothing but a power. Or if I know the voltage, square the voltage and divide with a R, what I am going to get is nothing but a power. So I can write as P is equal to either V into I, or P is equal to I square R, or P is equal to V square by R. Is it clear, class? Is it clear? So the maximum power delivered to the load by the source can be given as. So now I want to calculate the PM. So if P is the power, the maximum power is going to be PM. As I is the current, the maximum current is going to be IM. So P is the power, so maximum power is going to be PM is equal to IM square into RL. Why I am taking RL? Why I am taking RL is because I want to calculate the power that is delivered to the load. So it is going to be, that's what the maximum power delivered to the load by the source. So in place of R we are replacing the RL because we are finding out the maximum power delivered to the load by the source. So it is going to be PM is equal to IM square into RL. So name this as equation 1. Substituting expression of IM in the above equation. So PM is equal to, I am substituting IM, so it is IM square, so it is going to be VM square by square root of RL plus RX whole square plus XL plus XS whole square into RL. That's what your IM square into RL. In place of IM, I am substituting the expression of IM. IM expression is going to be VM by square root of RL plus RS whole square plus XL plus XS whole square. Am I right, class? So PM is equal to VM square and square root cancels with each other. So what you left out is RL plus RS whole square plus XL plus XS plus XL plus XS whole square into RL. So this is the maximum power that is delivered by the source to the load. Now I want to obtain a condition. What is the condition? ZL is equal to ZS star. ZL is equal to ZS star. So that can be obtained by differentiating this equation twice. One with a RL, another is with a XL. One with a RL, another one is going to be with a XL. Clear? Differentiating the expression of PM, nothing but a maximum power, with RL and equating it to 0. That means dPm by differentiation with respect to RL and equating to 0. If you see the expression of your PM, your expression of PM is VM square into RL by RS plus RL whole square plus XS plus XL whole square. Am I right, class? It is in which form? It is in the form of u by v. What is the differentiation of u by v? V into u dash minus u into v dash by v square. This is the formula, right? So in this expression, what is u? U is nothing but a Vm square into RL. What is V? V is nothing but the total denominator. So, and we need to equate to 0. So now dPm by dRL, differentiating with respect to differentiating the expression of maximum power, or differentiating the expression of Pm with respect to RL. So it is going to be V into U dash. So it is going to be Vm square into RL. This is U. U dash means d by dx of U. We are differentiating with respect to RL. So sorry class. Sorry. Right. So it is V into U dash. So RS plus RL whole square plus XS plus XL whole square into Vm square, because d by dRL by dRL is going to be 1, minus Vm square into RL into V dash. Yes class, V dash. So what is V? V is nothing but a denominator. So it is going to be 2 into we'll write right 2 into RS plus RL into differentiation. DRS is a constant. It's a constant. So DRS by DRL is going to be 0. Differentiation of a constant is going to be 0. Plus DRL by DRL is going to be 1. And this term is going to be anyway 0. Right. Shall we?
Yes.
This is V square. Is it clear? Vm square into RS plus RL whole square plus XS plus XL whole square minus Vm square into RL into 2 RS plus RL by RS plus RL whole square plus XS XL square whole square is equal to 0. Am I right, class? Yes, sir. So if I cross multiply, the denominator is going to become 0. So what you left out is Vm square into RL plus R square plus XS plus XL whole square minus Vm square into RL, or 2 Vm square into RL into RS plus RL is equal to 0. Yes? Yes or no? So this can also be written as Vm square into Rs plus RL whole square plus XS plus XL whole square is equal to Vm square into RL plus RL. Vm square gets cancels. Yes? Right. If I want to obtain the boundary condition, we need to differentiate this equation twice. One with respect to XL, other one is going to be with respect to RL. So what we will do is, we will differentiate this equation, differentiate the equation or expression with respect to XL first and equating to 0. Equating to 0 means dpm by dxl you need to perform, means you need to differentiate with respect to xl and you need to make to a means equate the equation to a 0. Now whenever I am talking about your Vm is nothing but a modulus of Vs of angle of 0 degrees or angle 0 degrees. Now this is constant, all these are going to be a constant elements, right? So it is in the order or in the form of a u by v. So we need to follow the standard expression for the d by dx of u by v. So dpm by dxl is equal to, it is v into u dash. So what is v? The denominator is v and the upper one is going to be u. So v is Rs plus RL whole square plus XS plus XL whole square, this is your v, into dpm by dx, means d by dxl of Vm square into RL. It is in the form of a uv. RL is constant and XL is also, Vm is also constant. Differentiation of the constant is going to be 0. So it is 0 minus u into v dash. So it is going to be Vm square into RL into v dash. So if I differentiate with respect to XL, the first term is going to become 0. Am I right, class? Because Rs plus RL whole square is going to be a constant, it's going to be 0. So 0 plus, here I am differentiating this expression with respect to XL, so it is going to be 2 into XS plus XL into XL is going to be dxs by dxl. XS is constant, so it is going to be 0 plus 1 by Rs plus RL whole square plus XS plus XL whole square, because it is going to be v into u dash minus u into v dash by v square, right? Now your equation is going to be, this entire term is going to become 0. So what you left out is minus Vm square into RL into 2 XS plus XL by the denominator. So that is Rs plus RL whole square plus XL plus XL whole square whole power square. Now once the differentiation is completed, I need to equate to 0. So it is going to be 0. So here, if I take the cross multiplication, something is 0. So it is minus Vm square or minus 2 Vm square into RL into XS plus XL is equal to 0. Yes. Then I can write as XS plus XL is equal to 0 by 2 Vm square into RL. Can I write? 0 by something is 0. So XS plus XL is equal to 0. I can write as XL is equal to minus XS. This is my condition 1 or a case 1. Is it clear, class? Yes, class. Fine? Shall I? Right. Now we will differentiate the same equation with respect to RL after substituting this first condition. If I substitute this condition of XL is equal to XS, so what happens is XL is equal to minus XS minus plus XS will cancel with each other. So the term that is going to be left out is going to be Vm square into RL by this term. Yes. Now you need to differentiate this with respect to RL and you need to equate the term to a 0. Now do the same story, that is it is also in the form of a u by v. So dPm by dRL is equal to Rs plus RL whole square into Vm square into dRL by dRL is going to be 1. Yes, class? Yes or no?
Yes, sir.
Right? So minus Vm square into RL. Vm square into RL is u into v dash. It is going to be 2 into Rs plus RL into, if I differentiate this, it is going to be 0 plus 1. Will you agree with me? Yes. By Rs plus RL whole square. Sorry, whole power 4. Whole power 4. This is v square. V is going to be RL plus Rs whole square. Whole power square is going to be power 4. Yes, class?
Yes.
Right. So now dPm by dRL is equal to, I will take Vm square common. Vm square, if I take a common, it is going to be Rs plus RL whole square minus 2RL into Rs plus RL by Rs plus RL whole power 4. Now after the differentiation, again you need to equate the equation to a 0. So when I equate to a 0, so what happens is, so if I am equating this term to a 0, if I cross multiply, denominator is going to become 0. So what you left out is Vm square into Rs plus RL whole square minus 2 RL into Rs. Minus of plus is minus, it is going to be 2 RL square is equal to 0. Yes, class?
Yes, sir.
Now we will keep this aside. Right. Now if I expand this expression, that is going to be RS square plus RL square plus 2RS RL minus 2RL RS minus 2RL square is equal to 0 by Vm square. 0 by something is simply 0. RS, 2RS into RL and 2RS into RL is going to be cancelled with each other. So then my equation is going to be RS square. Here one term is RL square. Here it is going to be minus 2RL square. So it is going to be RS minus RL whole square is equal to 0. This will cancel with each other. Here RS square, RL square minus 2RL square. So it is going to be RL square, not 0. So it is, then I can write as RS square is equal to RL square. Square gets cancelled. I can write as RL is equal to RS. This is my equation B. Clear? My equation B. Can I? Right? So you are very much clear that we are connected a load. The load that is connected to the source of a network, a circuit is going to be a ZL. You are very much clear that ZL is equal to RL plus JXL. From the equation A and B, we know that ZL is equal to RL is equal to RS and ZL is equal to, XL is equal to minus XS. So it is going to be minus J into XS. Whatever the source that we took, we assumed as RS plus JXS. But what we got is going to be RS minus JXS. If the sign of the imaginary part is going to be changed in the complex number or a complex quantity, it is called as a complex conjugate. So I can write as ZL is equal to ZS star. So Maximum Power Transfer Theorem states that the maximum power is delivered to the load by the source when the load impedance is equivalent to the complex conjugate of source impedance, or the required condition for the system to deliver the maximum power is going to be the load impedance should be equivalent to the complex conjugate of source impedance. You got the condition? Hence maximum power transfer theorem is going to be proved. Now, what is the maximum power that is delivered to the load by the source? You are having expression that is Pm is equal to Vm square into RL by RS plus RL whole square plus XS plus XL whole square. This is the expression what you are having. Yes, class, right? Now from these two conditions, RL is equal to RS and XL is equal to minus XS. If I substitute those two conditions, so Pm is equal to Vm square into RL by, I will substitute in the place of RS, RL. That is RL whole square plus in the place of XS or XL, we will substitute minus XS. Or you can write XS is equal to, XL is equal to minus XS, or XS is equal to minus XL. So anything is okay. So these two will cancel. So what you left out is Pm is equal to Vm square into RL. RL plus RL is going to be 2RL. 2RL whole square is going to be 4RL square. So 4RL square, RL square gets cancelled. So Pm is equal to Vm square by 4RL. Means when the circuit or a network satisfies this condition, what condition? ZL is equal to Z star. Or when the load impedance is equal to complex conjugate of source impedance, the maximum power that is delivered to the load by the source is equivalent to Vm square by 4RL. So this is about the statement of a maximum power transfer theorem and the maximum power that is delivered to the load by the source and the proof of the maximum power transfer theorem.